So this is just something I feel like I owe you to complete the course. Explain to you how the F statistic shows up. As I mentioned in my email today, it's a linear algebra exercise, but it's an important linear algebra exercise. They got all this to work out. In general, are there any broad questions about life in general, the world in particular, before we get going? We're going to try to, I know that Zhao Ying is busy trying to wrap up things, and we're going to try to get numbers to you quickly. She's at it. Everybody has their test scores back. I mentioned in my email to you that many of you worked very hard and did some impressive documents. So we live in a world where unusual things are happening, and so I wanted to acknowledge that by the last problem to show you that certain parts of the state are having a much more difficult life than other parts of the state, in particular the Indian reservations in the north, in the northern part of the state. It could be the case that Pima had a positive residual because of the Tona Otham here, although I haven't been able to verify that. There are issues in the sense that if you're poor, then you have to shop a lot. If you live in food deserts, then you shop in crowded places, and that may play a role. There's some indication that maybe a funeral in the Navajo reservation played an important role in the spread there, and there is some thought that in the Apache reservation that visitors from Phoenix went to Show Low. So all those things are trying to be verified now, and we'll see what happens, but I thought I would have you take a look at what's going on. Okay, so let's talk about the F statistic and where it comes from. Do this, okay. Oh, have I decided on a grading rubric? Not exactly. I have to look at the grades. So somebody asked me to have a grading rubric. So typically when we see the grades, there'll be natural breaks. So if you get 79, then it's almost certainly the case you'll get an A. If you have a 76, it's almost certainly, or B, excuse me, certainly you won't get an A, but I have to look at the exact breaks. And what'll happen is in the email that I send to you, we'll have total scores and the grade that would go down if I were to put a letter grade today. The other thing I keep getting asked, I guess, and I want to reiterate it since it seems to be helpful, is that this course for a variety of statistics options, the minor, the certificate, and any of the major programs, the master's degree and the PhD, require a B. That requirement is being waived for this semester alone, unless we face another circumstance like this, so that a pass becomes sufficient to satisfy the 566 requirement. So I hope that helps answer the question. So yes, there's 8 homeworks. So she is taking the 10 homeworks, and she's Zhao Ying is, and she's going to compute the top 8, and then give a grade. We have a Google sheet that we're putting together to try to help us figure things out. I may end up talking to her about borderline cases. So that's the way the grades are working now. So I gave her the link to that Google sheet yesterday with all of your first 2 test grades on. Okay. So the first 5 or 6 slides are really repeats of what a linear model is. That is, the response variables Y are linearly related to the data X through a set of parameters beta. So X is called the explanatory variables, beta are the parameters, and things are not exactly right. There are errors with respect to that perfect linear relationship those errors in the setup of linear models or general linear models is normally distributed with a fixed variance. We actually, after you do the theory of statistics, you're in a position to learn about generalized linear models, where the x betas are linked to the y's through some function that represents the mean of the values for y. So, for example, in logistic regression, x beta would be linked through the inverse of the logistic function. So y would be a number between 0 and 1, and it's meant to give you the probability of a 0 or a 1. And then y is binomial, or Bernoulli, excuse me, with that parameter that's coming from x betas. And then you do, in logistic regression, you do the optimization to figure out what beta is. And under the likelihood ratio framework, there you have to do things numerically. Here we were lucky in the sense that least squares estimation is the same as maximum likelihood estimation when we want to understand beta. So it's lucky meaning in the sense that the computation is easier. So there are 3 letters I want you to keep track of. I made a couple of typos. I hope I did this. So n is the number of observations, m is the number of parameters, and r is the number of constraints. So you can see that beta is an element of Euclidean M space. X has to take me from the parameters to the data, so X has to be n by m. You typically in these situations, although modern statistics is not constrained as to this, although it says much less, the number of data points has to be more than your parameters if you want to have a chance to do inference on it. And so X are my data, and they're normally distributed with mean vector X beta. So the likelihood ratio test for a hypothesis, which is some linear combination of the betas is 0 versus some linear combination is not 0. And we saw that for ANOVA, right? The A beta was that all of the Q means were the same, and A beta not 0 is that they weren't the same. And so in that case, if there were Q different categories for the analysis of variance, then A was a matrix of rank Q minus 1. So here it's R by M, and I said in for analysis of variance, the R was 1 fewer than the number of groups. And the critical region, which we also showed, was where some F statistic, when your data, you take the F statistic of your data, if it exceeds some critical value, then you reject. And that's what it was. So, and it's written in that way, and we'll learn as we go throughout this lecture why it's written exactly in that way. So we're going to look at something called a grand mean, or the mean of the null hypothesis, and we look at the data, the square distance of the data from the null hypothesis. We subtract from that the distance from the data under the alternative hypothesis, or under the whole parameter space. We divide it by that same quantity, and then there's a normalization factor, n minus m, the amount of data minus the dimension of the parameter space divided by the number of constraints in your hypothesis, in the linear model for your hypothesis test. And so if you looked at yk, the data minus the mean, then mu hat was the minimum vector under just the restriction that x was mu beta, and mu hat was the minimum value under the restriction that the mean was x times the parameters, and the parameters had this linear relationship to be 0. So it had one more constraint. So the likelihood function is 1 minus 2 sigma squared n over 2, and then because all these y's have mean x beta and variance sigma squared, and we can write it more compactly as 1 over 2 pi sigma squared to the power n over 2 e to the negative 1 over n squared times y minus mu transpose y minus mu. That's the way to write the sum of the squares. And the likelihood ratio, which we've seen a lot of times now, is you maximize the parameters beta and sigma squared under the null hypothesis. That is the case where a beta is equal to 0 and the response variables are linear related to parameter values, and then you take the soup over the whole space where the y is just linearly related to the parameter values. So for the numerator, we'll let beta hat be the maximum likelihood estimator for beta, and then by the invariance properties of maximum likelihood, we know that mu hat will be obtained, the maximum likelihood estimator for mu is obtained by just taking the data x and transforming beta through that. And then the maximum likelihood estimator for sigma, we've seen this in the past, it's just 1 over n. It doesn't have, it's a biased estimator, yk minus mu k. And again, we could write it as y minus mu hat transpose y minus mu divided by n. And that's what the likelihood looks like when you substitute it back in there, right? The likelihood has the y minus mu hat transpose y minus mu, both the numerator and the denominator, so you're left with only e to the minus n over 2. And then you stick in for 2 pi sigma squared to the power n over 2, the maximum likelihood estimate for the variance. You can do the same thing for the situation when the null hypothesis is true. Very similar things happen. It's the same equation with 2 hats on it. Then you take the ratio, right? So likelihood ratio test says that you would like the ratios of these. I feel like that should be n over 2 for the ratio of the sigma squares. So lambda naught is the critical value for the likelihood ratio test. It's the ratio of the sigma hat to sigma hat hat. It should be the power n over 2, I feel like. And so then when you take the 2 over n, negative 2 over n power and subtract 1, then you get the F statistic. And appropriately normalize it. And when we normalize that, we'll see in a few minutes, so that it becomes the normalized ratio of chi-squares, where each of the chi-squares are normalized in both the numerator and the denominator to have mean 1. So there it is. So this is just writing out what sigma hat hat over sigma hat minus 1 means, right? You'll find a common denominator to write the numerator is sigma squared hat hat minus sigma squared hat divided by sigma squared hat, and then I just expanded what that means. Okay, that's the test statistic. So now we know what the test statistic ought to be. The question is, what's the distribution of the test statistic under the null hypothesis? And so that's what we're going to spend the rest of the lecture doing, is just figuring that out. We're going to show you that the F statistic is a constant times the ratio of independent chi-square random variables. So that was sort of the magic. And we're going to do it through, I think, 12 properties, although I'm not exactly sure. So the first thing is we'll let the xi's, so I'm going to use Greek letters like crazy today. We'll get the xi's be the columns of x. And then these vectors are linearly independent. And why is that true? Well, I assumed it was true. So in other words, I'm going to use script L to be the span of those columns. It has dimension m. And the reason it's true is I told you at the beginning that x has rank m. So if x has rank m, then the columns of x have to be linearly independent. If they weren't linearly independent, then you would have to get rid of data that is redundant in order to achieve that ranking, that x has rank m. Or the parameters would be, and so the parameters would not be identifiable. I guess that would be the case. There'd be a linear relationship among the parameters that would be 0. Okay, mu is in that linear span. Why do I know that? Because mu is x beta, and x beta is equal to beta 1 times c1 plus up to beta, that should be beta m times cm. So mu is in script L because I can write it as a linear expression of the basis vector c1 up to cm. Okay, now when the null hypothesis holds, then I can write mu as beta 1 tilde eta 1 up to beta m minus r tilde eta m minus r, where the eta i's are in my linear span and the beta tildes are one of the components of beta. So this is where this could be real work. So I'll call L naught the linear span of those etas, eta 1 through eta m minus r. So this is where real work may have to happen. Right? You have this restriction, A applied to beta, the matrix A applied to beta, that gives you R independent homogeneous linear restrictions on the beta i's. And so you may have to do work for quite a while to eliminate R of those betas there's all linear operations. So when you do that, when you do eliminate R of the components of beta, then you're just doing linear combinations of the X's. And so by doing that, you'll get these etas instead of X's as the vectors that solve that equation. And you've gotten rid of R. So we'll let eta I be the linear combination of the Xi's that result from you eliminating the variables Xi from the, excuse me, the parameters beta from your equation. That's for the case of the null hypothesis. Okay, so that's 3. 4 is we say that this is obviously true that the vector space L naught is contained in L, and so that's true because we got that by constricting to the case where A applied to beta 0. So now I'm going to choose an orthonormal basis. So all 3 of the big letters come in, and alpha 1 through alpha n. So that is the orthonormal basis that takes care of all of my observations, which is an Rn if I have real valued observations. And I'm going to do that so that the first m of them is an orthonormal basis for L. We know it's m-dimensional. And from that, I'm going to take a subset of size m minus r that's an orthonormal basis for L naught. So I have the whole space that collects all the data that has orthonormal basis alpha 1 through alpha n. I have a slightly smaller space alpha 1 through alpha m. That's the orthonormal basis for the vectors that comprise my design matrix M, and then I have a smaller set of orthonormal vectors, alpha 1 through alpha m minus r, which form the basis of the subset of the parameter space under the null hypothesis. I call that L naught. And then I'm going to create a matrix P from that, where the kth row is alpha k. Then the claim is that PP transpose is the identity matrix. And if you look at PP, the k-th component of PP transpose, you take the transpose of the vector alpha k, and you take alpha L, and you multiply those together. Now, so that's the same as the inner product of the kth member of the orthonormal basis and the lth member of the orthonormal basis. And so if they're different, since it's an orthonormal basis, their dot product or inner product is 0. And if they're the same, their inner product is 1 because I've normalized it. So that's what's next. So it's 0 if k is not equal to L, and it's 1 if k is equal to L. So in order to build this under any particular circumstance, you may have to do a pretty serious computation, but abstractly, we can just talk about how to do it. Okay, so now we'll write the y's in this orthonormal basis, right? So we can write it as zk alpha k for some scalars, z1 through that should be zn, and we'll write mu as some linear combination of the alpha k's. Now mu is in script L, and so I know that I can write the vector mu as a linear combination of the basis of script L, and I'll call those vectors that give me that nu k. So I've done a lot of linear algebra, and all I've done is turn that into just new letters, zk for the y's and nu k for mu. And this follows because alpha 1 through alpha n is a basis for the entire space, and alpha 1 through alpha m is a basis for L. Okay, so now I want to look at y minus mu transpose y minus mu, and I claim it's the sum k goes from 1 to m of zk minus nu k squared. So for the first m components, I subtract off nu k. For the last n minus m components, I don't have anything to subtract. So let's see how that works. So if you take what I wrote on the previous page, y, which had all m components, that was k goes from 1 to n of zk's, and that gets split into 2 sums. One sum for the first m and another sum for the last n minus k. And then you have the nu k's, which nu k alpha k, whose linear combination gives me the vector mu. So you see the zk minus nu k times the basis vector alpha k only for the first m. Okay, and then I can write down y transpose y is a square of the norm of this vector. So since it's an orthonormal basis, then the norm of this vector is just the sums of the squares of those vectors. So zk minus nu k for the first m, and zk squared by itself for the last n minus m. Okay, so now maximization is easy. So property 7 tells you that mu hat is just the sum k goes from 1 to n of zk alpha k. Why is that? Well, if you look at property 6, you get to pick new k's in such a way to minimize y minus mu transpose y minus mu. And it's easy to see what to do. You just make the new k's, which is the only thing I have control over, equal to the zk's, and then that zeroes out the first m terms in my sum, and I have no control over the last n minus m terms. So that gives me the minimum value for mu, and that's mu hat. So mu hat is just the sum k goes from 1 to m of zk alpha k. Okay, yeah, so I write it down there. And so then y minus mu transpose y minus mu is just the sum of the last n minus m elements of that vector, because the first m have zeroed out by my choice of mu hat being zk times alpha k. Okay, so now if you want to minimize over all of L, that's what it tells you have to do for the denominator part of the likelihood ratio statistic. Make the choice nu k equals zk. So I've already discussed that. So that's how you got the minimum. Property 8 is you do the same thing for mu hat hat, but now you have to do it under L naught. So then you'll have the null hypothesis true, and so you're living inside of L naught, and so mu hat hat has to be a linear combination of the L naughts, and so you pick the new k's in that space to be equal to zk over the places where you have control, so it's up to m minus r, and then you get that y minus mu hat hat transpose y minus mu hat hat is just the sum of the last m minus r zk squares. So if you've done the linear algebra in a clean way, then mu hat and mu hat hat are simple sums of squares of the zk's. Okay, so now we can combine those to find property 9. So property 9 says that, so that's just going to be mu hat, mu hat hat, which is the sum over the zk squares from m minus r plus 1 at the end, and then mu hat, which is the sum from m minus 1 up to m, and then I have the same thing in the denominator. And then you can see that in the numerator, the sum starts at m minus r plus 1 and goes to n, and I subtract the last n minus m of them, so I only have to go from m minus r plus 1 up to m. So now my numerator and denominator sum the squares of the z over disjoint sets, right? Because the bottom one goes from m minus r plus 1 to up to m, and the top one, excuse me, and the bottom one goes from m plus 1 up to n. So and that's where the independence of the numerator and the denominator is going to come from. Okay, I've done everything with the z's, but my data is y, so I'm going to have to go from the z's back to the y's, and then back to the z's again, so how they're related to each other. So the next property is those z's that I got, which I got by taking the projection off of y. This is just multiplying them through by the alpha, y's by the alpha. It's just writing the y's, excuse me, in the basis vector of the alphas. And then the mean vector is just going to be projecting from mu onto nu. And the variance is sigma squared. So I have to take you through all that. Okay, so there's this is a linear transformation that takes me from the y's to the z's. And in that case, we've done linear transformations, or we've transformed densities under even nonlinear transformations. But under linear transformations, it's simpler. The Jacobian is simply the determinant. So the density for the z's is going to be the determinant of the inverse of that projection times the y value of the inverse of that projection applied to z. So you did that on the exam, except you did a nonlinear transformation. You used the exponential function. Here I'm using a multilinear, a linear transformation, but in higher dimensions. Now, because PP transpose is the identity, P inverse is equal to P transpose. And so the determinant of P inverse is equal to the determinant of P transpose. The determinant of P transpose squared is the identity because PP transpose is the identity. So the determinant of P inverse has to be +1 or -1, and it's just going to be, in some sense, based upon the orientation of the basis vectors. Is it right-handed or left-handed? So it's 1. Okay, so the density of z's is just going to be the density of y's applied to P inverse of z because the Jacobian matrix had determinant +or -1. Okay, so now we have to deal with P inverse applied to y to see what the exponent is in the normal distribution. So the y's are n-independent normal random variables with mean vector mu equals to x beta. So I'm just repeating what we had from the very first slide, and variance sigma squared. So there's its density, right? 1/2 sigma squared to the power n/2 e to the minus 1/2 sigma squared y minus mu transpose y minus mu. So that's just independent normal random variables with mean mu and variance sigma squared. Okay. But now I'm going to write the y's in terms of the z's. So y minus mu transpose y minus mu. Well, y is just P transpose z, right? Z is py, and so if you multiply through both sides by P transpose, since P transpose is equal to P inverse, then you get y is P transpose z, mu is P transpose nu. So that gives you both sides of the equation. Now, there's a transpose for the first factor, and the transpose says that I reverse the order of terms. So it becomes, so I can factor out a P transpose in front of the z minus nu. So I have P transpose times z minus nu, all that transpose. And that becomes z minus nu, there shouldn't be a transpose there, z minus nu times P transpose times z minus nu. So PP transpose is the identity, so I just get z minus nu transpose times z minus nu. So the random variables z are also multivariate normal random variables with mean vector nu and variance sigma squared. Okay. Now under the null hypothesis, mu is in L naught, so I have to figure out the distribution of this test statistic under the null hypothesis. And so under the null hypothesis, the new k's are 0 for all the k's that are big enough. But if you remember the test statistic, the only k's that I look at are those that are bigger than m minus r plus 1. So all the ones that I care about have mean 0. So consequently, each of the zj's up to zm have mean 0. And I can write the test statistic as k goes from m minus r plus 1 to m in the numerator, and k goes from m minus 1 to n in the denominator. So those are summed over disjoint intervals. These are independent normal random variables, each with variance sigma squared. So I can divide the numerator and the denominator by sigma squared, and I get the sums of the squares of standard normal random variables. So the numerator is a chi-square random variable. The denominator is a chi-square random variable after I've divided through by sigma squared. So I have the ratio of independent chi-square random variables. Okay, the numerator has r degrees of freedom, right? Because I have r terms in there. I'm going from m minus r plus 1 to m. And the denominator has n minus m degrees of freedom, right? Because I'm going from m plus 1 to n. So that sort of does it. Now recall that a chi-square random variable has mean L. So the constant factor that is traditional in the F statistic is chosen so that both the numerator and the denominator has mean 1. Okay. Now there's one more thing you can do the F statistic to make it even more compact. You can write it as k goes from m minus r plus 1 to m of mu hat minus mu hat hat in the numerator, and in the denominator things stay exactly the same. So I've collapsed those two terms in the numerator down to 1. And so if you look at it this way, the F statistic is the ratio of the between group variances, right? So that So mu sub k is the variance for each group. I'm sorry, mu sub k is the estimate for the mean inside of each group. Mu sub k hat is the variance, is the estimate for the mean overall. So I'm looking at the difference between the means inside a group as opposed to between groups. Okay, and so the idea, if this is big, you reject, and if it's not big, you don't reject. So that it was the, so if you go back to the very beginning, when I talked about analysis of variance, and I showed you these 3 different box plots, then I said the basic idea of analysis of variance is, if I look at the center line differences between those box plots, is that big compared to the width of the box plots? So the center line differences between the box plots is considered in the numerator of this, right? It looks at the mean of each of those box plots as opposed to mean overall. Is that big? And then the bottom, the yk minus mu k squared, is looking at the width of each of those box plots. And then typically we divide the top by r for the number of different box plots, and we divide the bottom by n minus m to give the total amount of data. Okay, so we can get this straight from properties 7 and 8, right? U hat is the sum k goes from 1 to m of zk alpha k, and mu hat goes from k goes from 1 to m minus r of zk alpha k. So I can just subtract those two, and I just get the sum that goes from m minus r plus 1 to m of the zk alpha k, right? The rest of the terms go away. And then I can take the norm of that. Well, the alpha k's again are an orthonormal basis. So the norm of the vector mu k minus mu k hat is just the sum of those of those k's, m minus r plus 1, going from m minus r plus 1 up to m of the zk squares. And that's exactly the term that we had when we computed the f statistic to get the chi-square distribution, so that the numerator had m minus r degrees of freedom. So we did that computation just to get ourselves off the ground, and we can see that it gives us an interpretation of the f statistic as a ratio of the between group variance to the within group variance. No matter what sort of linear model you're looking at, if you appropriately interpret between group to within group, you can make this work. Okay, so if you look, the F distribution has 2 numbers that are associated with it. So we say 2 degrees of freedom parameters, N1 for the numerator and N2 for the denominator. And if you want to, you can write down the chi-square distribution for N1 degrees of freedom and N2 degrees of freedom. And then you can look at the transformation, looks at the ratio, let's say for one of them, and then you can create a two-dimensional distribution, one in the ratio and one for one of the chi-squares. And then you can use the Jacobian of that transformation, very much like we did with the t-statistic. You can integrate out the marginalized to find the F distribution. And if you do all that, this is what happens. You get 1 over the beta function, and then you have this sort of linear ratio n1 minus x over n1 minus x plus n2 to the power n1 over 2, and then 1 minus n1 minus x over n1 minus x plus n2 to the other power times 1 over x. So that's just the outcome of all of the calculus that gets you the F distribution. So after Gauss had figured out the t distribution explicitly 110 years ago or so, it wasn't so hard after that to use the same sort of calculus ideas to get the distribution for the F statistic. Okay, so that's quite a linear algebra exercise. It's impossible to sort of absorb all that at once, but if you want to, you can take the time and you can read through these notes. You can see how cleanly it fits together. Somebody worked very hard to create a very clean strategy to build the F statistic. So I'll leave you with that formula and the beauty of that formula as a way to end the semester. So I want to thank you all for taking the time to pay attention and follow through to the end. I said early at the beginning of the lecture, but I'll say it again at the end of the lecture, the care that many of you showed in working out the details of that exam showed that you took the course seriously and that you worked hard, and that you're much further along in understanding of the theory of statistics than you were when you began, and that is my goal, to get you there. The semester ends now. We'll have some communications between now and the next few days on how you've done on prosaic things like your grade, but now you're closer to being professional statisticians by a long shot than you were back in August, and I congratulate you for all that you've learned. And going forward, I hope you will stay in touch with me so that I can see how your progress is going. And so, so you're welcome. For both of you, for all three of you, when I told I was talking to the provost last week, and I said, I said my class is keeping me busy. It takes a while to prepare these lectures and do these things, but I said, but it is the one great thing that I get to do inside of all this stuff that makes sense. There is a quote that I'll paraphrase from Bertrand Russell. He used to ask the question if he did more mathematics or less mathematics during the time of war, and his answer was, I did more mathematics. And I asked him why, and they said, because you need to go to a place where the rules apply. And I think that's sort of a useful thing here, because things are sort of crazy now, but mathematical ideas are a stabilizing force in this world, and it helps us make sense out of crazy times. And so you guys and I are better equipped at trying to understand those things. So I'm going to spend this afternoon trying to help people make better tests for the COVID virus, and to see if we can do a better job to making everything safe for all of you and for ourselves as well. So we learn things that are really useful. So that's all I have to say right now, and I thank you for all your kind words that have come streaming across the chat over the last few minutes. It was a good thing that I was asked, what should I say about teaching online? And I think the answer is, it would have been much harder if I had not met you first. So we had a semester and a half together to sort of become acquainted with each other. And so the last half of the second semester, you were people that I knew, and so I felt comfortable talking to you. If it's a whole year of not knowing and meeting each other, I think it would be a lot more difficult. So it was a joy meeting and getting to know all of you. So we'll leave it there.